Now we want to bisect the external angle, which is shown here. This angle equals 2 pi minus the original angle theta. Let me show how I do it. So this solution shows both bisections, internal and external. So first we divide external angle by 2, then we continue division, and finally we come to some conversion solution, and I can show it here. If we have the initial angle approximately 2 pi over 3, which is 120 degrees, then after two bisections we will have the angle equal to 1 pi, 180 degrees, and we can continue division and come to this solution. Since we already know that bisecting the angle in such a way that I did in this problem will result in the angle trisection, we can find the final steady state solution, which is this one, in easy way. This solution equals, let's go to the math. To prove this geometric result, we will repeat the same process we did before for internal angle and compute the steady state solution and transient solution using sequences and geometric progression. This time the initial interval of angles will be from theta to 2 pi. So theta 0 equals theta over 2 plus pi. Theta 1 is the middle angle between theta and this first division. So theta over 2 plus theta over 4 plus pi over 2. This time we will have two sequences. One sequence involves theta and another sequence will involve pi term. So when substituting into recursive formula previous angles, I will group it in two sequences right away. We can see the process. I add previous two terms together and divide it. I will have the following sequence. I group theta terms and pi terms together and divide by 2. And we see the following pattern. For each sequence grows in one term each times, and this will be two geometric progressions. If we move the initial term of these both progressions outside the parentheses, we see that the remaining part of progression coincides. So the first initial term is theta over 2, and for the second progression the initial term pi over 2. We move both outside and the remaining progression is the same. Just for pi term we have one term less than for theta term, but at infinity it will be negligible. So we see the decreasing geometric progression with this initial term, and common ratio is 1/4. and here to the power of k. I can represent this geometric progression as two sums, because the second sum has one element less than previous, and when computing transient solutions we must keep notice on it. Theta 0 term equals theta over 2 plus pi. But if we let n to go to infinity, then we have bounded value, and the sum of terms of geometric progression equals common ratio divided by 1 minus initial term divided by 1 minus common ratio. And after some arithmetic, we get the same solution as we did geometrically. Now I want to improve this recursive formula to make it dependent only on one previous term. And to do that, I will repeat the same process that I did for internal angle, but some arithmetics may be different. And I also will make educated guess that the formula must have the following form. Initial angle theta plus pi and minus 1/2 of previous term. I also will start from the top to the bottom. So for theta 4 we already have calculated results. I grouped theta terms and pi terms together, not separately. And this time I want to collapse these formulas, because this series does not give us enough information to prove our guess. So we have two terms, one involves theta, another involves pi, 21 over 32 and 11 over 16. I will represent both these formulas in such a way to show that it depends on the previous term. We have already computed the previous term. Theta 3 equals the following. So if I put this theta 3 results into the recursive formula and do the arithmetic, you can see that I will come up to these rational numbers near theta and near pi. And more specifically, for theta we have 32 minus 8 minus 2 minus 1, and for pi we have 16 minus 4 minus 1, which gives us these rational numbers we wanted to. So the formula proved. For theta 4 and theta 3 depend on each other like that. We will do another iteration and prove the same result, the same formula for theta 3 and theta 2. We already have these values represented as a series. I collapse the formulas. I put the previous result into the recursive formula, do some arithmetic, and we see that the rational numbers will be the same. So the formula is correct, and this is our formula. Now let's repeat this graphical exercise in GeoGebra. So we see that solution alternates and finally converges to a steady state solution, which we get geometrically and proved algebraically. Also make notice that for auto angle, the solution converges from one side only. If you have recursive formula dependent only on one previous term. But if you have a recursive sequence dependent on two terms, we have alternating solution. And let's check also on algebra view results for auto solution. Here is the formula, auto iteration list. We have initial term, which is constant, and only one independent variable, and m iterations. And the angle at infinity is the same as we proved. We see it in red here. So if I delete auto solution, we will have only internal. That's it. You can find the link to this GeoGebra solution under the YouTube video, and also you can find the link to overleaf solution where I show typesetted LaTeX formulas, and you can also download a PDF document.